So in this session, we'll do the live coding on gate level modeling that we have explained so far. So I will do the following projects. First, I will implement an 8:1 multiplexer that we have already described. I will do the implementation as well as I will write the test bench to check the functionality of this multiplexer. And then I will move to 3-stage decoder and write a test bench for it to check the functionality of it. Here I will explain a decoder with and without enable signal and what is the advantage of decoder having an enable signal. And then I will move to 4-bit triple carry adder with test bench. Then I will compare the design with different FPGA board. The same design I will dump into different FPGA boards and see the utilization of resources and power consumption having in different FPGA boards. Then I will give a example of gate delay also, and we will see the simulation result how the gate delays will affect the output of your design. So let's start by creating a project in Vivado. So our first project will be 8:1 multiplexer. So I will define the project mux 821. I am doing all these steps so that you will also practice with me. The more you practice, the more you get habituated with Vivado. So the target language will be Verilog, and I want to create a file. I want my file name should be mux821. Okay, and then next, I'm not adding any constraint file as of now because I don't want to do the implementation. I want to just run the simulation. So I'm selecting a Jetboard. Next, and then let's start writing the code. I will define the input output ports in the code itself. So I'm clicking yes. So now my source will appear. This is my source. Double click, it will open. I'm minimizing this. So here I will write what are the different IO ports that I have. My output is, let's say, out, comma. Always remember we will write the output port first and then the input ports because it is easy to remember while you call the module. So out is my output and have, since it is an 8:1 multiplexer, let me comment. I want to design is design and 8:1 mux. So number of inputs are from I0 to I7 and have control signals are S0, S1, comma S2, and output as OUT. Okay, I'm defining the same things here. I0, I1, I2, I3, I4, I5, I6, I7 are my inputs, and then control signals S0, S1, S2. Then I'm closing the bracket, semicolon. Now the port declaration is done. It is red because we have declared the port, but we haven't specified what are these ports, whether they are inputs or outputs. So I'm defining output as my output port, semicolon, then input as my I0 is 0 or O, this should be 0, I0, I1, I2, I3, I4, I5, I7, comma S0, S1. These are my input ports. Now see, once I define the input and output ports, there is no syntax error. Your module is complete, but we haven't added any functionality here. We have only defined a module. Now if you do the synthesis of this, it will create just a black box without any functionality. So it will create 3 input pins, 8 input pins and 3 control signals and 1 output pin, but there is no functionality inside this. So let's write the functionality Once the port declaration is done, we have to see whether if there are any internal wires are required or not. If you remember, the multiplexer will require both the true signals of the control signals as well as the complement signals also. So if you remember, we have drawn 3 true signals as well as the 3 complement signals. So I was writing those as the intermediate signals. Intermediate signals. So in case of intermediate signals, I required wires of S0 bar. I want S0 bar as my complement output of S0, S1 bar, comma, S2 bar. And same thing in the multiplexer, if you remember, the diagram has 8 AND gates and each AND gate has their own partial outputs. So we have to define those partial outputs also. So the partial outputs I am defining from P0 to P1, P2, P3, P4, P5, P6 and P7, right? These are my partial outputs. Now I will write the functionality of my functionality of my 8:1 decoder, 8:1 multiplexer, sorry, 8:1 mux. So for this, I need to create the functionality using logic gates, right? Because this is gate level modeling. So first thing is I want to get the complements of the control signals. So I am using 3 NOT gates like this. NOT of, I can either give the name N1 or N2, whatever name I want, but since we are using the primitives, as I already told, for primitives you don't need to define the names. You can directly write NOT of what you want output S0 bar, right, from input S0. Done. So this will create S0 bar from S0, which is an inverted signal. Same thing, we'll copy and paste. We'll copy and paste for the 3 NOT gates like this. We want S1 bar, S2 bar from S1 and S2, right? Once these are done, we'll require partial outputs, right? The partial output is the end of S0 and S1. So I'm adding end of the first partial output will be coming from I0, comma, S0 bar, comma, S1 bar, comma, S2 bar. So if all the three are 0, 0, 0, then I0 will be mapped to P0. That is what this line means, and with semicolon. Now copy this 8 times so that you can write for 8 different partial outputs: P1, P2, P3, P4, P5, P6 and P7. So once you have defined, you have to define the outputs also. P1 should come from I1. Similarly, these things from I1, I2, I7. So the combination to get P1 is S0 bar. I am taking this as MSB. So 0, 0, 0, 0, 0, 1. This will be 1, and 0, 1, 0, and 0, 1, and 1, and this will be 1, 0, 0, 1, 0, 1, and 1, 1, 0, and all are ones, right? I am saying 1 means true signals, not complement signals. Once you have the partial sums, all you need to do the OR operation between all the partial sums to get the output. P0, P1, P2, P3, P4, P5, P6, P7, Pi. No P8, so P7. See how easy it is to define a 8:1 multiplexer. All you have done is you defined 3 NOT gates to get the complement outputs of control signals. and 8 AND gates to get the partial outputs, and then the final output is obtained by ORing operation, right? So what you have learned, you can define any number of inputs to a gate. It will automatically create based on the number of inputs. Here it will create a 4 input AND gate with an output of P0 and 4 inputs. Always remember the first term is the output. Similarly, it will create out as the output signal with 8 different input OR gate. So this is my design, and we have AND module already written. So the design is complete. Now we need to write the stimuli. Stimuli means test bench for this design. So before writing the stimuli, let's see the elaborated design of this. Let's save the design and run. Let's see how does the design will look like. We are generating the netlist. Let's do it in background, and by that time we'll create a stimuli source. You know how to add the source. Left click here, and then okay, since it is background, it is happening, it is not adding. Yeah. Now this is the schematic, right? As we expect, we thought it will create a complete 8-bit AND gate, but it is creating using 2-bit AND gates. So that's why there are a lot of AND gates involved, but the output functionality is similar to whatever we have designed in theory. Okay. So let's add the source of add source. We want a simulation source. Simulation source. I want to create a file. Let's call this as top module, top underscore mux. Okay, then finish. So it is creating a top, and I don't require any IO ports, so directly clicking OK. Yes. Now I will write the test bench here. This is my top block. I don't have any IO, so I'm directly terminating the module. And then here I will declare the variables. So first one is we have to declare the variables, right? So we have to consider reg for inputs. Let's say my inputs are from I0, I1. If I write same I0, I1, you will get confused. So I will write 7 different inputs: A, B, C, D, E, F, G, H. We need 8 different inputs, right? 1, 2, 3, 4, 5, 6, 7, 8. 8 inputs, as well as we need 3 control signals also. So let's say the control signals are CS0, S1, S2, and then net. Now we require output. Output should be wire output. There I have written out. Here I am writing output and semicolon. Done. Now you need to call your. No, you cannot give output, right? Because output is a keyword. So you have to specify some output underscore marks. Now you have to call your design module. What is the name of the design module? Mux 821. So same name you have to write Mux 821, and then you should definitely write a name here, otherwise it won't instantiate. Because it is a user defined module, you have to write the name. So I'm writing Mux1 as the name. And then if you remember the order, what is the order? First one is output, and remaining all are inputs and control signals. So in the same order I'm calling my output is mapped to output underscore mux, comma my inputs are mapped to these inputs. Let's see, then close bracket, semicolon. Now you have called the module. Let's see whether it is really calling it or not. Save it. Now you see the top module is calling the mux 8:1 with a name of mux1, right? Whatever name you give, it will appear here. So it is calling properly. Now what you need to do is apply the inputs. So applying inputs. Inputs. So how to apply the inputs? We need to use the initial block. Since we have multiple lines, we have to start with begin and then end the initial block somewhere here. Between these, we will write the different combination of inputs. So the initial begin. So let's set the inputs like this. What are my inputs? A is equals to 0, let's say, comma or semicolon we have to use. B is equals to 1, semicolon. C is equals to 0. I am giving some random inputs. A, B, C, D is equals to 1. D, E is equals to 0. C, D, E, F, C, right? H. So these are my 8 different inputs I have set. So if I turned on S0, S1 control signals all zeros, then my output should pass the A, which is 0, right? So let's give the control signals also. Before that, let's display the inputs once so that we can see the inputs in the output window also. So let's take a delay of 1 nanosecond and display the inputs. Display. We can use display or monitor based on our requirement. So I'm displaying the inputs are A is equals to percentage B since they are binary numbers, comma B is equals to percentage B. Same thing I will write A, B, C, D, E, F, G, H, and then slash n to get the new line. So I have to specify in the same order A, B, C, F. So I will display the inputs. After this, let's choose different sequence of S0 and S1s to get different ABCs. So to get A as my output, what is the sequence I need to give in S0, S1, S2? CS0 should be equals to 0, CS1 should be equals to 0, and CS1, and this is CS2 should be equals to 0. This combination will result into this, right? Now I will display my output at this C. So after 10 nanoseconds, I am displaying the output at CS0 equals to percentage B, comma CS1 is equals to percentage B, comma CS2 is equals to percentage B. The output at CS0 is, I need to define my output, right? Is percentage B quotation. Now I have to define in the same order CS0, CS1, CS2, comma. I want the fourth one, this percentage B should be mapped to my output marks. Output underscore marks. Done. So this is one particular combination you can get for different combinations like this. Let's say I will do for only 4 combinations and we'll see whether it is working or not. Changing 001 case, 010 case, and 011 case. The first four outputs should print A, B, C, D, right? 0, 1, 0, 1, it should print. Or we'll do the all the 8 combinations just by calling this. So 0, 0, 0, 1, and then 1, 0, 0, 1, 0, 1, 0, 1, 1, 1, 0, and 1, 1, 1. So we'll get all the possible outputs. We have already entered the initial block. So let's save this and do the simulation. Run simulation, run behavioral simulation. Now we got the output. So this is the different control signals that we have controlled. Since we haven't changed the input is always constant, but control signals we have changed. So based on the control signals, the output is, let me zoom here. Let's take at this time period, the control signal is all 0, then the A output will come. A is already 0, so the output is mapped to A. In this case, what is the combination? 0, 0, 1. In 0, 0, 1 case, it should follow the output of B, which is 1. Correct. Same, let's take here. Here, the combination is 1, 1, 0. So, sixth input. The sixth input is G is equals to 1, which is equal to my output. So, same thing you can see in the window here itself. See, the inputs are A, B, C, D. We have defined these inputs, and the output at 0, 0, 0 location is mapped to A, which is 0. Similarly, the output at 1, 0, 1 fifth location, which will be 1, 2, 3, 4, 5, 6. Sixth location, right? 1, 0, 1. Sixth location is 1, seventh, eighth. Eighth location is also 1, 1. So the same things are appearing here. 0, 1, 0, 1, 0, triple 1. This is the combination I gave. 0, 1, 0, 1, 0, triple 1. This is the combination I got. So my multiplexer is working as intended. So this is the simulation of a multiplexer. Let's do one more project. In this project, we'll create a 3:8 decoder. The decoder and multiplexer will look almost similar. In the case of decoder, you don't have any control signals. The input itself will act as a control signals, and it will decode the 3 input signals into 8 output signals. So uh, we'll create a decoder project and we'll see the output of decoder. Create new project. Next, so I'm creating a decoder 328. Next, create a file. I'll call deck 328. Next, next, select jetboard. Next, and finish. Would you like to close? No, I want to have this code also so that I can copy and paste here. Okay. So now this is my project summary. It is creating. It was created. Let's close this and start writing the code. So in case of decoder, how many inputs are there? There won't be any control input, so I'm copying as it is this up to here. And since we haven't defined the input output ports, it is in red signal. So I'm defining the input output ports. We don't require these control signals, so I'm deleting them. Declaration is done. After declaration, we don't need this, but we'll require the inverted of these inputs. So I have to write wire of these inverted ones. So I will write like this. Wire, I need complements of all these inputs. So I am writing wire I need complements of all these. E, P, right? After this, what I require, I will have 8 different AND gates, and then I just need to map those AND gates to these combinations. Before that, I need to obtain these signals, right? To obtain these signals, I need to use 8 and NOT gates like this. I0B should come from I0. Similarly, I have to get all the 8 outputs from 8 different inputs: I1, I2, I3, I4, I5, I6, I7, I7. Similarly, I1, I2, I3, I4, I5, I6, I7. Once I got all these things, I'll directly write my output values using AND gate. And of my output is, okay, I'm doing reverse. Actually, in decoder, you'll have 3 inputs and 8 outputs, right? So 3 inputs and 8 outputs you'll have. 3 is to 8 decoder it is. That's why you should always write what you are doing. I'm designing 3 is to 8 decoder with 3 inputs as I0, I1, I2 and 8 outputs as O0, O1, O0. O is very bad, so we'll write out 0, out 1, so on up to 7. So out 0, copy, we'll have 8 outputs: 1, 2, 3, 4, 5, 6, and 7. We don't require all these things, only 3 NOT gates are sufficient. Similarly, 3 wires are sufficient. So since why it is giving red signal, because we have defined lot of extra ports and we haven't defined their port directions. So I am defining them. Control V. Now I need to write out 0 will be from I0B, comma I1B, comma I2B, right? All 3 0 0 0 condition is mapped to out 0. Same thing I need to write for 8 times. Out 1, out 2, out 3, out 4, out 5, out 6, out 7. 0 0 0 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, then all 1. Right? Our definition of decoder is done. Save it. And let's see the design of the decoder. We'll continuously follow the same steps so that we'll get habituated to it. Whenever you design something, you always check the design and see whether it is really giving the output that you require. See, I require an output 0 which needs to be mapped from I0, I1 and I2. Right? So the I0, I1 are getting multiplied here, that will be get multiplied with I2 here. In the design phase, we have used 3 input AND gates, but here they are using only 2 input AND gates with 2 stages. The first stage will decode I0, I1 and the second stage will decode I0, I1 with I2. So ultimately your output 0 will be having I0 bar dot I1 bar dot I2 bar. That is what you require here. The same thing will come here also. The circuit is proper. It is using 3 inverters as expected to get the complement values, and it is properly connected. Right, now let's write the test bench for it. So I am adding the source, add source, simulation source, create file, top underscore decoder, finish. Okay, so let's copy the test bench from here. Maybe few lines will be useful from here. Will require register and outputs, right? Wires. Let's open the simulation source. We don't require this. Okay, now tell me what will be the registers and what will be the outputs. Register should be my inputs. So my inputs are these three. I'm giving with same name so that you will understand that the names in Verilog are local to the module. Even if I give same names, it will still work because the names here will be local to this particular module and names here will be local to this particular module. We'll see whether it will work or not. So these outputs I will define as a wires. Done. And then what we did, we called the multiplexer in that case, and we'll call the decoder here. Decode 3 to 8, and then give a name, decoder, my decoder, whatever name you want. But you should definitely define the name because this is a user defined module. You have to define the module names for user defined module. So my decoder, and you have to follow the order. Here the order is from out 0 to I2. Since I have given same names, I can directly call that here. Close the bracket and semicolon. Right. Then we have to apply the different input patterns. So how to apply the input patterns? Take this example like this. Take the different output patterns, input patterns. It should be in initial and begin. So I have to, that's why it is giving red signal. I have to write initial, begin. Right? Initial, begin. And the names, it is saying that these names are undefined, obviously because they are not defined here. So these names I need to replace with I0, I1 and I2, right? So what I'm doing, I'm directly using a find and replace thing. So you can use replace or control R, you can directly press, and what you want to find, all the CSS you need to change with I, right? So I'm finding this is the first CS it found. So replace, you can do like this, or you can do replace all. So all of them got replaced. Let's save this. Now we'll apply the different input patterns. So we'll follow the same steps. Initial, begin, and inside this we'll display the inputs and output combinations. Let's write the input combinations. I0 is equals to 0, I1 is equals to 0, I2 is equals to 0. The outputs at I0 is equals to 0, 0, 0, or whatever the combination, or here there will be 8 outputs, right? Out 0 is equals to is the output, comma out 1 is equals to is the output, comma out 2 is equals to the output, comma let copy 0 1 2 3 4 6 7, right? So in the same order we need to give here what is the names out 1 out 0 out 1 out 2 like this, right? Copying this out 0 to out 7. Done. Now I will do the same thing for different combination of inputs. 1 3 4 5 6 7 0 0 0 0 0 1 same 8 possible combinations we'll see and check 0 1 0 0 1 0 0 1 0 1 1 0. Let's save this. It's done. Either we can verify the output here or here. See how beautiful it is generating the outputs, right? These are the possible input combinations we have given. At 0 0 0 it is taking the I0, which is what we have defined I0. The I0 is 0, right? I0 is 1. At 0 0 case the output 0 will be 1. Let me zoom in. At all 0 case only output 0 will be 1. Similarly at 0 0 1 case output 1 will be 1. Similarly at last case all ones case the output 7 will be 1. So this is the functionality of decoder. With this decoder you can use to decode the different rows of the memory. So what does this mean is in the first clock cycle up to 10 nanosecond the output 0 is high and remaining all the outputs are high. From 10 to 20 nanoseconds output 1 is high. Similarly 20 to 30 nanoseconds output 2 is high. Let's see, right? So it is a staircase kind of function that we have obtained from the decoder. So as I explained, there is one more extra thing that you can do. What is that extra thing is I want to add the enable function also. Why do I require enable function? Since the decoder will always give me the output based on the inputs, right? This is the combination circuit. But I want my decoder output should appear only if I apply the enable signal. For that what I need to do? I just need to modify my circuit little bit like this. Beforehand we have a decoder like this and these are coming through the inputs, right? So this is mapped to 0 0 0 case. This is my out 1 and these are my I0 I1 and I2. I want to add one more extra signal called enable signal. Whenever this enable is equals to 1 then only I want my output should appear. So what I need to do, I have to connect this output to all of these AND gates. So what does this mean? When the enable is 1 then only this will execute and pass the output through output, right? For this I need to add one extra signal in my design as well as in my stimulus file. So I am adding one more input called enable comma en. I need to declare it as an input. I don't require a en bar, so I am not declaring. And here I will add enable in all the AND gates. Hmm. So let's save this in the stimuli file. We'll add the same thing. We need to have one more register called enable, and then call that enable here. Now in the beginning state itself, let's say I have defined my enable is equals to 0. But after some time, let's say after this, what is this case? 101 case, I will define my enable is equals to 1. Let's see what happens. Save, run the simulation. As you can see, I have given my enable after fifth signal, right? This is 0 0 combination 1, 2, 3, 4, 5. So after 101, then only my output starts appearing. Until then, my output will be 0. My output start appearing for these three cases only. So this is how you can control the decoder also by using an enable signal. Right? So we have did 2 experiments, and we will do 2 more experiments. Like we will design a ripple carry adder, and the main thing I want to show in this session is I want to dump the same ripple carry adder design in different boards and see how much power it is consuming on different boards. And I will tell you how to add the boards that are not available in Vivada also. So first thing I want to show you is how to add different kind of boards. Till now we are only selecting the jet board, right? But if I want to add different boards, how to do that? So for that, you need to download the boards that are provided by Xilinx and Disilin.